And these are the candidates. So.
And this technique is classical?
Oh yes, everything is classical until I indicate it's not classical anymore. So here again is the algorithm. Input, ODE, output, a basis of the vector space of all its rational function solutions. So first you take the leading coefficient, that means the polynomial in front of the highest order derivative in the equation, and let's call them P1 up to Pn. So you have to factorize there. And then for each of them you determine the maximum possible multiplicity by the techniques that I skipped in the interest of time. And then you know every possible rational solution must look like this. Some polynomial divided by, well, the product of the factors that can occur, each raised to its appropriate multiplicity. Okay, and then you know the denominator, so maybe you overshoot, because maybe there's one rational solution with this denominator and another one with this, but it doesn't matter, because if you put here too much, this too much will show up in the U and cancel out in the end, so that doesn't matter. So it's maybe too much, but it's certainly enough. And then from the given ODE for f, you construct with this pattern here an ODE for the u. And then you use the algorithm from the first part to find the polynomial solutions of this auxiliary equation. And for each polynomial solution, u, this f is a rational solution of the given equation, and vice versa. They are on to borrow correspondence. Questions? Yeah?
What does ansatz mean?
Oh, ansatz means like you set up a template for the solution. Ansatz is a German word which Doran likes to use a lot. But I don't know, how do you explain what ansatz is to people who don't know it?
It's
an educated guess.
Framework.
An educated guess. Okay, thank you.
Oh, okay.
So,
That's a good one.
yeah, okay. So it's clear what it is?
Yeah.
So you say every solution must have this form, and there are still some parts which you don't know. In this case, the u.
So given the general idea, you're trying to find specifics from that general idea.
No. So you say you're searching for a solution, a rational function solution.
Yeah.
For a rational function solution, you need a numerator and a denominator.
Yeah.
And a priori, you don't know what it is.
Yeah.
Now you make an ansatz by saying, okay, I still don't know what it is, but I know parts of it. So you know the p's at this point of the algorithm. So you say, okay, I'm searching for a rational function solution which has this form,
Okay.
an unknown numerator,
Yeah.
and then a denominator which I know very well, which I know explicitly.
Yeah, so your guess educatedly that it has this particular form.
Okay.
But there's
So-
still something to be found.
So
the U has to be found.
So you reduce the problem of finding a rational solution to one of finding a polynomial solution, which at that point is still undetermined, but it's a simpler kind of solution because that's only polynomial, and you know how to do this.
Yeah.
Yeah. Okay?
Yeah.
Okay. And that's all I want to say about rational functions. Questions about rational functions? Everything clear? Good. And now comes the exciting stuff. Let's talk about hyperexponential functions. So I said already, in the first slide I only had an example. Now here is really the definition. A hyperexponential function or expression or term, as you like, is by definition a solution of a first order equation. So f is hyperexponential if there are two non-zero, I think I should say, polynomials, p and q, such that f satisfies this equation. And so it's very easy to find hyperexponential solutions of first order equations because the equation itself describes it. Now what we have...
So there are no constraints on the degree of p is to be bigger than q,
No.
so as anything
No.
goes.
Anything is allowed. Okay, so we know from calculus how to solve this in closed form, and in fact every hyperexponential expression can be written in closed form, but if you just do what you have learned, so you do a separation of everything is f on one side, everything is p and q on the other side, integrate, and then you get a log of f there, you exponentiate, then you have f expressed in terms of the p and q. So p and q are polynomials, that means you can even evaluate this integral in closed form because rational integrals can be evaluated. So the closed form of a rational integral is always a rational function plus a linear combination of logarithms, like this. So this is a rational function. And here's the linear combination with some constants, gamma, of a log of some polynomials. And because this is all sitting inside of an exponential function, we can break this apart and write this sum inside the argument as a product of x of frat times a product over x of log, and x of log cancels each other, so the result is then something that looks like this. So this is what you should imagine when somebody says hyperexponential function. It's an exponential of a rational function times a product of several polynomials raised to some constants. So you see it splits into two parts. This part and this part. And I will call this part the exponential part and this part the rational part. More or less. So the intuition is that this is kind of a rational function, except of the gammas need not be integers. So if you think of the gammas as integers, then this is a rational function. In general, they are not integers, so that's not really the official definition, but it's the right intuition. This is the exponential part, this is the rational part. So here's the official definition if you're interested. We care about whether two hyperexponential functions are similar. So we say they are similar if their quotient is a rational function. And then this is an equivalence relation among hyperexponential terms. And we say that the equivalence classes under this relation, they form the exponential part of a given term. So here are some more fancy examples. This and this is equivalent because the quotient is a rational function. The square root of 2 cancels out and there remains a 4. 4 is an integer, that's nice. So they are okay, they are equivalent. They have the same exponential part. Those ones we say they do not have the same exponential part, even though on both sides it says x of 0. But the square root of 2 and 2, they are not at integer distance. And these ones anyway, they have different exponential part because here there's an x and there's not. So this is obvious, this is also obvious, and this is a technicality that you can neglect if you want. Okay, and then the task is the same as before, more or less. We are given again a differential equation, something like this, linear with polynomial coefficients, and the task is to find the hyperexponential solution. In this case, there are two hyperexponential solutions, this one and this one, and because the equation in this example has order 2, every solution can be written as a linear combination of those two. In general, of course that's not the case, but I didn't want to make a bigger example. So in general, you will have, typically you will have no solutions of this form, but then we want the algorithm to tell us there's definitely no such solution. So the question is how can we find them? And the idea is similar to before. We reduce it to something that we already know. In this case, we reduce it to rational function solving. And we can do so if somebody tells us what is the exponential part. So if we know that, let's say, we are looking for a solution that has this exponential part and then some rational function, then we know very well what the derivatives of f look like, because we can differentiate this as many times as we want and get expressions that depend on very explicit stuff and the derivatives of u, which is an unknown rational function at this point. So here's what it looks like. It's u prime, u prime prime, u prime, u not known, and there are some rational functions that appear from differentiating the stuff. So they enter here, but it doesn't matter what they really are, because we can compute them explicitly as soon as we know what the exponential part is. Okay, and then you have again an ansatz, yeah? Because we assume here, we know it has to look like this with an unknown rational function. So you plug this into the differential equation, and then it happens that this here appeared, this exponential part appeared in every derivative, so I can cancel it out. And what remains is an equation which we understand very well. It's a linear differential equation with polynomial coefficients for the unknown rational function u. So I use the algorithm from before to find its rational solutions. And every rational function u gives rise to a hyperexponential solution of the original equation with this prescribed exponential.